Hello everyone, I am Chetan Rajoria. I am from the Department of Mechanical Engineering, ABES Engineering College, Ghaziabad, and I welcome you all to this video lecture. In this video lecture, we are going to discuss a numerical problem based on equilibrium of forces. So let's come to the problem directly. So students, this is the problem which we are going to discuss here in this video lecture. 3 bars hinged at A and B and pinned at B and C, as shown in the figure below, form a 4-linked mechanism. Determine the value of the force P that will prevent movement of the bars. Also calculate the forces transferred in the bars AB and BC. So this is the problem. This is the diagram of the problem which we are going to discuss here. This is basically a simple 4-bar mechanism in which the angular displacement of this link AB causes the movement of the bars BC and CD respectively, or it can revert its direction of movement also. So now you can observe point, or you can say the junction B and the junction C are experiencing two forces, 500 Newton and P newtons respectively, and the direction and magnitude of these forces are in such a way that it is going to prevent any type of movement of this 4-bar mechanism. Okay, the movement of this mechanism is not possible. So in this problem, first of all, we will find out the value of force P as well as the forces which are being transferred into these bars AB, BC and CD. So let's proceed. First of all, we will start from this junction B, because the force is having the magnitude of 500 Newton and this magnitude is completely known. So we will start from that junction where the value is given. So let's analyze this junction B first. Now, we have already discussed that the forces are acting in such a way that there is no movement in this mechanism. So if we observe this mechanism carefully, we can clearly conclude that each and every member of this mechanism is experiencing a sort of compressive forces. AB, BC and CD. All these 3 links are going to experience a compressive nature of force. So if we draw the free body diagram of this junction or pin joint B, how we are going to find the forces which are acting on it. So let us see. The first force is 500 Newton, which is given here. The inclination from each and every adjacent member is given here. Now, the force which is transferred from point A onto point B will be in this direction, like this, because AB is under compression. So the compressive forces are shown generally like this. Therefore, the reactive force will act in the opposite direction. So this is the force which is being experienced by point B because of the force in this link, means from point A towards point B. This is the force, and we can show it as F A B. Force from A towards B. Similarly, the force which is being transferred from point C onto point B can be shown like this in the direction of this link BC, and we can symbolize this force like F CB. So FAB is acting from point A towards point B, and it is acting in the direction of this link AB, and FCB is in the direction of BC, and this force is acting from this link at point B, from point C towards point B. So let's draw this free body diagram separately for better understanding. This is FAB. This is FCB. And this is the known force, the force which is already known to us. And the magnitude is 500 newtons. Now, using the basic geometry of this figure, we can calculate the intermediate angles between these three forces. Point B is under static equilibrium under the action of only these three forces. So let's calculate the intermediate angles between these three forces. We can see here that this angle is 65 degrees. Therefore, the remaining angle, because A, B up to this point, this is clearly a straight line, and this angle is 65. Therefore, the remaining angle here, it should be 115 degrees. Means 180 minus 65 degrees, which is equal to 115 degrees. Now, what will be the value of this angle? You can see this angle is 45 degrees, and this is a straight line. CB up to this arrowhead, this is clearly a straight line, and this angle is 45. Therefore, the remaining angle should be 135 degrees. Now, we know that this complete angle is 360 degrees. Out of this 360, this one is 135 and this one is 115. Therefore, the remaining angle is 360 minus 135 minus 115. So this remaining angle is 110 degrees. So this is the individual, you can say, a free body diagram of this junction B, okay, which I have shown here separately. Now this is a three-force system under equilibrium, static equilibrium. So we can directly apply the Lamy theorem. So let's apply the Lamy theorem. 500 upon sine 110 degrees is equal to FAB upon sine this angle 135 degrees is equal to FCB upon sine 115 degrees. First of all, let's consider the first two terms. Using these two terms, we can calculate FAB, that will be equal to 500 sine 135 upon sine 110 degrees. FAB is equal to 500 sine 135 degrees upon sine 110 degrees. So it's coming to be 376.24 newtons. So that's our first answer. The force which is being transferred in this link AB is 376.24 newtons. This is our first answer. Now, let's consider the first and the third term. 500 upon sine 110 degrees is equal to FCB upon sine 115 degrees by considering the first and the third term and this Lamy theorem application. By this, we can conclude that FCB is equal to 500 into sine 115 degrees upon sine 110 degrees. By calculation, we can find out that the value of FCB is 482.23 newtons. So this is our second answer, you can say. The force in this link from point C towards point B, this force is F432.23 newtons. So far we have considered this junction B, okay, the forces which are acting at this junction B. Now in the second step, we will consider the forces which are acting on the opposite junction, the second junction, which is the junction C. Let's consider the forces which are acting at this junction C. First of all, this is the unknown force P. We are going to find this value. Now, previously, FCB was the force which was acting from point C on point B. Now we will consider FBC, the force which is being transferred from point B on point C. So we can show this force like this, FBC. Previously, that was FCB. Now we are writing it like this, FBC, from point B towards point C. Magnitude-wise, this force will be equal to FCB. There will be no difference in its magnitude. Only the symbol is different because it is acting just opposite to the previous one we discussed earlier. Second force is transferred from point D towards point C. So we can show it like this because this member is also under compression. So we can show this force like this. And it can be symbolized in this way, FDC. FDC is the force which is being transferred from point D towards point C. And each and every member had already discussed here earlier is under compression. So we can draw this free body diagram separately for better understanding. Let's draw the free body diagram of this junction C. This is FDC. Second one is FBC. And this one is the unknown force P, which needs to be calculated. But FBC is equal to FCB. What is the value of FCB? Let's see. FCB is 482.23 newtons. So numerically it is same. 482.23 newtons. It is already known now. Yeah. Now it is once again the condition of static equilibrium for three forces. So once again, we can apply the Lami's theorem for simplicity. But before application of the Lami's theorem, let's calculate the intermediate angles between these three forces. We can observe that this angle is 50 and this is 45 given in the diagram. So the total summation of this force, or you can say the total summation of this angle is 95 degrees. Now this angle will also be equal to 95 degrees because it's just opposite angle. So we can show it. This angle is equal to 95 degrees, the summation of 50 and 45. Now what will be the value of this angle? We can observe that this angle is 45 degrees. So the remaining angle will be 90 minus 45, that is 135 degrees. It is 135 degrees because this angle is 45 and this is a straight line. Therefore, the remaining angle will be 135 degrees. Now, the complete angle around a point is 360 degrees. We already know this. Therefore, the remaining angle can be calculated by 360 degrees minus 135 minus 95. So it is coming to be 130 degrees. So these are the intermediate angles at this junction C. Previously, that was the junction B. And now we are considering the second junction C. Let's write the statement of the Lami's theorem here. FBC upon sine angle of opposite forces, means sine 135 degrees, is equal to P upon sine 95 degree is equal to FDC upon sine 130 degree. FBC is known. So let's consider the first and the third term first and the second term first. P can be calculated using this expression. P is equal to FBC into sine 95 upon sine 130 and 5 degrees is equal to 482.23 multiplied by sine 95 upon sine 135 degrees. By calculation, we can conclude that this value P is equal to 679.38 newtons. So that is the third answer. Now consider the first and the last term. First and last. So let's write FBC upon sine 135 is equal to FDC upon sine 130. Implies that FDC is equal to FBC multiplied by sine 130 upon sine 135 degrees. By calculation, we can conclude that FDC is equal to 522.42 newtons. That is the last one, the fourth answer. So in this way, in this problem, we calculated all the forces, all the unknown forces, the force along this link AB, the force along the link BC, the force along the link CD. All these three forces are compressive in nature, as well as this unknown force P. To maintain this mechanism in static equilibrium, it's not going to move under the action of this force system. So that's all from this problem. Thank you so much. Thank you so much for joining this session.